Good morning, students. Chapter 4, Moving Charges and Magnetism. Yes, in last lecture we have discussed about Biot-Savart law. Okay, due to current carrying conductor, how magnetic field is produced. How magnetic field is produced. See, students, if you know chapter 1, 2 and 3. Chapter 1, due to charge, electric field is produced. Then assume types of charges. Point charge, system of point charges, linear charge, surface charge, volume charge, due to one cylinder, due to one sphere, due to one shell. What is electric field? So due to different charge distribution, how to find electric current, electric field, that we have discussed. Now similar type we can think in magnetic field. We know that current carrying conductor produces magnetic field. So now current carrying conductor, if they are in different shape and size, then what is magnetic field? What is magnetic field? We know Biot-Savart law, but it is for current element. It is for current element. Okay, so yes, here how to understand this? Magnetic field on the axis of a circular current loop. Magnetic field on the axis of a circular current loop. See, here it is one circular current loop like this. Here it is one circular current. Okay, it is its center. Its radius is R. It is its axis. On axis, at this point, let me want to find what is magnetic field. Current flowing from this circular ring is I. Current flowing from this circular ring is I in this direction. In this direction. Okay? Okay? So now see, we have one circular current loop of radius R carrying current I. Okay? And yes, it is its axis. It is its axis. Okay? We want to find magnetic field at this point. From this center O, its distance is x. So it is your question. Okay? One circular loop of radius R carrying current I. Okay, one circular loop having radius R and carrying current I. And yes, it is only one circular loop. Only one circular loop means one turn. Numbers of turns. Only one. Yes. And what is question? You have to find magnetic field on axis at distance x from center. Find magnetic field. Find magnetic field on axis at distance x from center. At this point, you have to find what is magnetic field. Now see, direction is important. This circular loop, actually, yes, limitations are there, okay, to draw three-dimensional object. It is as shown in figure. This part is outside and this part is inside. Means if I have one ring, it is like this. Okay, it is like this. And current is flowing in this direction. Current is flowing in this direction. Actually, this ring is placed like this. And current is flowing in this direction. Clear about this? This outside facing towards you, current is moving in downward direction, and this side it is moving in upward direction. Now how to find? With the help of Biot-Savart law. How? First of all, I will divide this whole circular loop in very small elements. First of all, I will divide this whole circle in very small elements. At this point A, I am taking one very small element like this. One very small element. It is very small element. And yes, as current is flowing in this direction, as current is flowing in this direction, okay, this current element will be ideal. This current element will be ideal. Clear about this? Take one element having length dl at point A. Clear about this? Yes, we will write. See, take one element having length dl at point A. So current flowing, yes, current flowing will be same. So here current element is ideal. Here current element is ideal. So yes, here current element is ideal. Now I will find magnetic field at this point due to this current element only. Let from this point it is position vector. Yes, you have to displace this point like this. Yes, you can. Okay. So yes, it is position vector r. That its distance is r. Clear about this? Okay. So yes, current element is ideal. Okay. Distance, like this point P. Distance of point P is r. Okay. Clear about this? Then what is magnetic field at point P due to this current element? Magnetic field at point P due to element dB is equal to, yes, we have equation mu 0 upon 4 pi current element ideal sin theta is angle between ideal and r. See, ideal, in this figure I have drawn this ideal in this direction, but actually it is in this direction, perpendicular outside. Again, this circular loop is like this. So this ideal, it is in this direction. Because here current is coming outside. See, current is coming outside. So here this ideal is in this direction. R is in this direction. So yes, you can say, sir, this R is perpendicular to this ideal. So what is angle between them? Angle between them is 90. So this ideal sin 90 upon R square. Clear about this? How this angle 90? Okay, so dB is equal to, it is mu 0 upon 4 pi ideal upon R square. Now it is only magnitude, students. It is only magnitude. What about direction? We cannot add magnetic field directly. Because it is vector quantity. Yes, it is vector quantity. So now you have to find direction of magnetic field. Equation. Remember equation. dB is equal to mu 0 upon 4 pi ideal cross R upon R cube. Yes, you know this equation. Okay. How to find? dB is in direction of ideal cross R. See here. Ideal outside. Yes or no? Ideal outside. R is in this direction. Yes or no? Yes. Again, ideal, it is perpendicular to what coming outside, and R is in this direction. Then how to find the direction? See, it is plane containing this R and ideal. Ideal is outside. So first of all, put right hand in direction of ideal. Wrap your fingers towards R. But see, as this plane, we know that resultant magnetic field dV is perpendicular to both ideal and R. So if plane is like this, it is R and it is ideal. Then magnetic field will be perpendicular to it in this direction. Clear about this? So yes, due to current element at point A ideal, magnetic field at point B dB, it is its magnitude and direction is as shown in figure. Clear? Now see, it is dB in this direction. Now I will resolve this dB in two components. Okay, resolve dB in two components. Resolve dB in two components. Which two components? See, first component in this direction and another component in this direction. This component is called parallel to axis and this component is called perpendicular to axis. So yes, resolve dB in two components. One parallel to axis and another component perpendicular to axis. Now to find component, yes, we need angle. So yes, I am assuming this angle is phi. Or yes, you can also say theta. Okay, so if this angle is phi, then yes, obviously this component becomes dB cos phi and this component becomes dB sin phi. Clear about this? Okay, so parallel to axis component is dB cos phi. Okay, and perpendicular component is dB sin phi. Clear about this? Again, one circular ring carrying current I, radius r, axis at distance x, at point P, you have to find magnetic field. Take point A, current element ideal, distance r from this element, magnetic field dB, its direction dB, resolve dB in two components, parallel to axis, perpendicular to axis. Clear about this? Okay. Now I am taking another element opposite to A and identical to A. It means if A is here, its diametrically opposite point B. A opposite B. Okay. So yes, identical element means if length of this element is dl, length of this element is also dl, then yes, see, here current is coming outside, here current will go inside. So yes, here current element is in this direction, it is IDL, in this direction, it is IDL. Clear about this? Okay, so yes, identical to A, you have to take one element at B. Clear? Now identical and diametrically opposite means if from this point you draw position vector, from this point you draw position vector, yes, then this distance is also R. Yes or no? This distance is also R. Yes, this distance is also R. Clear about this? So now see, current element is same. Yes or no? Yes. Distance is same. Yes. Then the magnitude of magnetic field is also same. Clear about this? Then see, take identical element at diametrically opposite point B. Okay, then magnitude of magnetic field dB, yes, it will be same, that is mu 0 upon 4 pi IDL upon R square. What about the direction? See, here IDL is perpendicular inside, R is in this direction, so theta will be perpendicular to it. Again, IDL is inside, R is in this direction, so theta will be resultant magnetic field will be in this direction. Again, perpendicular to plane of R. Yes, it is like this. R is in this direction, current is going inside. Yes or no? Then ideal R, thumb, it is perpendicular to this plane. And perpendicular to this plane means what is direction of dB? dB is in this direction. Clear about this? Okay. Yes, These two elements are identical, distance is same. So yes, if this angle is phi, this angle will also become phi. Again, resolve this dB in two components, parallel to axis, perpendicular to axis. Yes, as this angle is phi, this component will again become dB cos phi. This component will become dB sin phi. Clear about this? Yes, we have considered two elements at A and B. Due to A, magnetic field dB, magnetic field dB. Due to B, their magnitudes are equal, but see direction. So yes, we have to resolve in parallel and perpendicular components. From figure it is clear. See, perpendicular component of magnetic field due to A and perpendicular component of magnetic field due to B. They are in opposite direction, and yes, their magnitudes are equal. So yes, they cancel out each other. They cancel out each other. Clear about this? Okay, but their parallel components, they are in same direction, so they never cancel out each other. So what is conclusion of these two elements A and B? Yes, I have this whole wire and I have considered only two elements A and B. You have to resolve, you have to take numbers of elements, and for this element we will have another diametrically opposite element at this point. Yes or no? So yes, due to these two elements, again perpendicular component will be cancelled out, parallel component will be in same direction. Due to this and this element, again perpendicular component will be cancelled out, parallel connection they will be in same direction. So yes, you have to write only one statement as shown in figure. Resultant of perpendicular component is 0. At this point P, magnetic field is only due to parallel components of magnetic field due to each element. Clear about this? Remember case of electric dipole on y-axis on its equator. Simply do that. Okay, so yes, here now you have to write one statement. Which statement? See, here it is. How to write? Okay, as shown in figure, we can say resultant of perpendicular component, perpendicular component is 0, or they cancel out each other. Yes, you can also write that statement, they cancel out each other. So therefore at point P, resultant magnetic field is only due to parallel components, Clear about this? Is only due to parallel components. Okay, so resultant magnetic field at point P, resultant magnetic field at point P. B is equal to integration dB. Why integration dB? See, dB cos phi. Yes, B is equal to integration dB cos phi. dB cos phi. Why integration dB cos phi? dB cos phi. Parallel component of magnetic field due to A. dB cos phi. Parallel component of magnetic field at P. Similarly, if you take each and every element, their parallel component, they will be in same direction. Same direction means you can add them directly. Clear about this? Now, B is equal to integration. What about dB? Yes, we have equation of dB. dB mu 0 upon 4 pi I dl upon r square. I dl upon r square. Okay, cos phi. Yes, how we put value of cos phi? See in figure. This angle is phi. Yes or no? This angle is phi. Observe this in figure. This angle is phi. Okay. Yes, this angle is phi. Then Then see, here it is. If this angle is phi, we know that this magnetic field is perpendicular to plane of R, so this angle becomes 90. This angle becomes 90. Yes or no? This total angle is 180. This is 90. It is phi. So obviously this angle will become 90 minus phi. It is 90. Then this angle will become, yes, it is phi. Yes, it is phi. Clear about this? Clear about this? Again, this angle phi we have assumed. DB is perpendicular to R, 90. Then this angle will be 90 minus phi. 90, this angle is phi. So cos phi, see cos phi, how to find cos phi? Cos phi is equal to, cos means adjacent side upon hypotenuse. Adjacent side upon hypotenuse. Phi its adjacent side is R and hypotenuse is R. Yes or no? R upon R. Cos phi is equal to R upon R. So here, how to write it? It is R upon R. Clear about this? Clear about this? Then is equal to, it is integration mu 0 upon 4 pi I dl R upon, here it is R cube. Here it is R cube. Clear? So yes, now we have to simplify this. How to simplify? We will see. We will understand what is method. What is method? We have to take two elements at A and at B. We have to write equation of magnetic field, draw direction of magnetic field, resolve in two components. From that figure you can easily understand perpendicular component will cancel out each other and resultant magnetic field is only due to this, that is called parallel components. Okay, now see another one value we have to put. What is relation between, see what is given, this smaller is not given, we have assumed. What is given? Only this data. Circular loop, radius r, current I, number of turns 1, and horizontal distance on axis is x. So yes, we have to eliminate this small r. How to eliminate this small r? How to eliminate this small r? Yes, from figure you can say, sir, there is one right angle triangle. It is r, it is x. So what is r? What is r? Yes, this r is equal to, it is under root r square plus x square. It is under root r square plus x square. Yes or no? Yes, it is x r. Then it is under root r square plus x square. So yes, you have to put that value here. You have to put that value here. Okay. It is equal to integration mu 0 upon 4 pi I dl r upon r cube. And what is r? R square plus x square. Root means I can write this as r square plus x square raised to 1 by 2, and its cube means how to write? It is r square plus x square raised to 3 by 2. Clear about this? Now last step. Mu 0 constant, 4 pi constant, current flowing from each and every element same constant, outside. R radius outside, R constant, X point we have fixed, and from center its distance is also fixed. So yes, mu 0 upon 4 pi I R upon r square plus x square is to 3 by 2 constant. You will have only integration dl. Yes or no? You will have only integration dl. How to write? We'll see. Now see. B is equal to, yes, mu 0 upon 4 pi I dl r upon r square plus x square raised to 3 by 2. Yes, B is equal to mu 0 upon 4 pi constant I r constant upon r square plus x square raised to 3 by 2 constant, integration dl. Now, what is meaning of integration dl? Integration dl. If you have this figure, dl. What is addition of length of each and every element? Circumference of circle. Yes, it is circumference of circle. So you can write B is equal to, here it is mu 0 upon 4 pi IR upon r square plus x square raised to 3 by 2, and here it is 2 by r. Clear about this? What is dl? Length of element. length of this element plus length of this element plus length of this element, it will be circumference of circle. This 2 pi r. Clear about this? Yes, this 2 pi cut, and here it will be only 2. The magnetic field B is equal to, it is mu 0 I r square upon 2 r square plus x square is to 3 by 2. 2 r square plus x square is to 3 by 2. Yes, you have to remember this equation. You have to remember this equation. Clear about this? Clear about this? Yes, you have to remember this equation. B is equal to mu 0 I r square upon 2 r square plus x square is to 3 by 2. Where what is each and every term? Mu 0, medium is air. I, current flowing from circular loop. R is radius, and x is distance of that point on axis from center, Clear about this? Clear about this? If yes, here I have only one term, but if I have n terms, I have one loop having n terms, 1 turn, 2, 3, 4, 5, 6, 7, n turns. And yes, radius is r, current flowing is I, Then what is magnetic field on axis? What is magnetic field on axis? Then simple. Due to one loop, due to one turn, magnetic field is this. Due to multiply. Okay, so yes, due to n turns, magnetic field is B is equal to mu 0 n I r square upon 2 r square plus x square raised to 3 by 2. Okay, so for n turns you have to remember this equation. For n turns you have to remember this equation. Clear about this? Okay, now special cases. First case, at center of coil, or at center of loop. See, what is meaning of center of loop? I want to find magnetic field at point P. Then yes, from center to this point we have some distance. But if I am taking this point here, then what is value of x? 0. Then x center, x is equal to 0. Then put in this equation, x is equal to 0. What happens? See, B is equal to, it is mu 0 n I r square upon 2. Here it is, r square plus 0 raised to 3 by 2. r square raised to 3 by 2. Square and square root, they will cancel out each other, and here it is only r cube. So it is mu 0 ni r square upon, here it is 2 r square and square root, so it is r cube. R square plus cube. So what is your answer? B is equal to, it is mu 0 ni upon 2r. So yes, it is equation of magnetic field at center. It is equation of magnetic field at center. Clear about this? Clear about this? So yes, it is how to find magnetic field at center. Yes, we can also find one another equation. Which equation? See, if x is very greater than r, means this point P is at very large distance comparative to its radius. Then see what you have to do. As x is very greater than r with comparison to r, in denominator you have to make like this r. Then what happens? See, B is equal to mu 0 ni r square upon 2. If you ignore this r with respect to x, then what happens? X square raised to 3 by 2. Then yes, it is x cube. Yes, it is x cube. Clear about this? Okay, so yes, it is magnetic field due to current carrying circular ring, circular loop, circle, whatever. Okay, and these are two special cases. Clear about this? Yes, it is one important equation. It is one important equation that will be used in this chapter. Okay, also these special cases you have to remember. This equation, based on this equation, there are numbers of equations. Okay, so what is difference between these two equations? That you have to remember. If you know this equation, you can easily detect the special cases. Okay? Right now.